All right, it looks like we are up and good to go. So what I'd like to do is solve a couple of questions that you all have passed along to me at the email. So if you do have any questions during the live stream, you can send them to mathquestionshelp. All right, it looks like we are up and good to go. At gmail.com. So if you can, send a screenshot of whatever question you'd like to work out there so I can read it from my other monitor. I'll bring them up, all the info that we need to help you solve that question. I'm going to start working through a couple questions from Math 111. This is my Math for Arts students. So the question here, if you do have the textbook, it is question 2.54. And that question asks us to find an equation of a line that satisfies the following conditions. So we know that the x-intercept is 3. We know that the slope of this line is -5/3. And the question wants us to get that line in ax plus by equals to c form. And typically, these values are whole numbers. So if you are having some discrepancy with what the book says, just try to convert these a, b, and c values into whole numbers and double check and see if that's what the book has. Okay, so let's try to convert some of this stuff that they are giving us. So the x-intercept is 3. I would like this as an ordered pair or a point on my line. So in this case, the x-intercept would be given as 3, 0. And now with that, I should be able to figure out the equation of this line using y equals mx plus b form. So they've given us the slope, which is -5/3. And we know that the x-intercept is 3, 0. And we need to use that to figure out the value of b. Okay, so in this case, 3 divided by 3 gives me 1, and I'm going to be left with -5 plus b over on the right-hand side. My left-hand side is still 0, and adding 5 to both sides gives me b is equal to 5. So I can go back and finish up my mx plus b form. It should be -5/3x plus 5. But I do want to convert this into standard form, ax plus by equals to c. So the easiest way to do that so that I have a, b, and c being whole numbers is to multiply all of these terms by 3. That's going to get rid of this fraction here in front of the x. So multiplying y by 3 gives me 3y. Multiplying -5/3x by 3 gives me -5x. And multiplying 5/3 gives me 15. Finally, I'm just going to move the 5x over to the left-hand side. So we have 5x plus 3y is equal to 15. Yes, that would be one potential final answer for this question. Okay, we're going to continue along in Math 111, looking at questions 2.67 and 2.68. For those of you that are just tuning in, if you do want to send your questions to mathquestionshelp@gmail.com, I'll take a look at those and we'll solve them here on the live stream together. If you can, include a screenshot so I can get all the info for the question that you'd like me to solve. So let's take a peek at 2.67. 2.67 deals with converting between Celsius and Fahrenheit. So it gives us the freezing temperatures of Celsius and Fahrenheit at 0 degrees and 32 degrees. It gives us the boiling temperatures of Celsius and Fahrenheit at 100 degrees and 212 degrees. And then it wants us to figure out a linear equation that's going to relate Celsius and Fahrenheit together. So what I might start by doing here is converting both of these into ordered pairs. So if I do 0, 32 and 100, 212, now I have two possible ordered pairs that are on this conversion line between Celsius and Fahrenheit. And we can use these two ordered pairs to figure out the slope of our line as y2 minus y1 divided by x2 minus x1. Okay, so just give me a moment here to rifle this through a calculator and see what our slope is. So 212 minus 32, that's 180. And I'm going to divide that through by 100. It's going to give me a decimal number 1.8. Okay, so now we have our slope and we actually have our y-intercept here as well. So if you're paying attention, this is our b value if we use mx plus b form. Okay, so the only thing that we need to kind of be careful of here is what is x and what is y. So in our ordered pairs, the Celsius value came first, so I'm going to replace the x with a capital C. Our slope was 1.8, and our y-intercept was 32. And the y values, both of the second numbers in our ordered pairs, were Fahrenheit numbers. So what this is going to do is this is going to give us a conversion between Celsius and Fahrenheit, where I input a Celsius value and I get an output that is Fahrenheit. So the last part of this question asks us to convert 25 degrees Celsius into Fahrenheit. So I can now input 25 in for my capital C and simplify this to get some value in Fahrenheit. So let's see what we get. I get 77. Okay, so 25 degrees Celsius is about 77 degrees Fahrenheit. Now 2.68 is very similar. It just says to swap the order of the ordered pairs and get something that's going to convert from Fahrenheit into Celsius. In fact, if we know the relationship up here, we should be able just to solve for C and get what we want. So for 2.68, that's where I'm going to start. I'm going to start with this conversion that we know. And let's subtract 32 from both sides. And then divide both sides, or all three of these terms, by 1.8. So f divided by 1.8 minus 32 divided by 1.8. That'll equal capital C. And so if you want, you can simplify this a little bit. Over here with the f, this is really like 1f divided by 1.8. So 1 divided by 1.8, that gives me about 0.55. Okay, I'm just going to round that up to 5/6. And then 32 divided by 1.8 gives me about 17.78. So these aren't particularly splendid fractions or decimal numbers to deal with, but there it is. And then the second part of this question is just asking us to convert 72 degrees Fahrenheit into a Celsius value. So now I can input 72 into here. And figure out what that is in Celsius. So 0.56 times 72 and subtract 17.78. So I got something that's about 22.54 degrees Celsius. All right, so that finishes up our first couple questions in the Math for Arts Students course. The next question I have is from an upper year calculus course, and that is dealing with some parametric equations. So a couple of questions being asked here, given these two parametric equations. So parametric equations just allow us to convert back and forth between Cartesian coordinates and some other coordinate system. We want us to find the derivative of y with respect to x. We want to find the second derivative of y with respect to x. And then it's curious about for what values of t is our curve going to be concave up. All right, so for those of you just tuning in, remember, if you do have any questions that you want me to go over, send them to mathquestionshelp@gmail.com. And if you can, include a screenshot, and I will do my best to get through a couple of those tonight. Okay, so looking at my formula book here for upper year calculus, I can find dy by dx by looking at the following ratio of taking the derivative of y with respect to t and then dividing by the derivative of x with respect to t. So the derivative of y with respect to t is 1 plus 1 over t. And the derivative of x with respect to t is 1 minus 1 over t. Now it looks like we might be able to simplify this a little bit. So let's see if I can find some common denominators here. So maybe t over t for my ones. And it looks like this is going to simplify to t plus 1 divided by t minus 1. So there is our first derivative. If we want to get at the second derivative, it's going to feel a little bit different than taking a second derivative normally. What we're going to do is actually take the derivative of the first derivative with respect to t, and then we're going to divide by the derivative of x with respect to t. Okay, so we already know what the derivative of x with respect to t is, so I'm going to bring that down here in the denominator, 1 minus 1 over t. Now the derivative of y over x, or our first derivative with respect to t, is going to be a little bit more complicated. So I need to use the quotient rule here, derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. So we're going to get this beautiful fraction, and hopefully this is going to simplify to something nice. So let's take a look up top. So I'm going to get t minus 1 minus t minus 1. Okay, and you might as well simplify this denominator 2 to t minus 1 over t, just in case something's going to simplify here. Okay, so up here looks like we're going to have t subtract t to give me 0. So I'm going to have negative 2 over t minus 1 squared. And this is all divided by t minus 1 over t. So I just want to get rid of this kind of dual fraction business that's going on. And I'm going to flip and multiply. So I'm going to multiply all this by t over t minus 1. So it looks like our fully simplified second derivative is going to look something like this. And so kind of returning back to our original question, we want to know for what values of t our parametric curve is going to be concave up. So essentially what we have to do is look at all of the critical values for this particular curve. Oops, I'm missing a t up here. So we look for where is the numerator equal to 0. That's going to be when t is equal to 0. And we're also going to be concerned where our second derivative is undefined. So that's where our denominator is equal to 0. And that's going to happen when t is equal to 1. So we have two critical points. Actually, I kind of lie. They're called critical values. They may not necessarily be critical points. But we're going to need both of them inside of our second derivative chart. So we need 0, we need 1. And we're going to look at test values that happen for values, say, less than 0, values that are bigger than 1, and say values in between 0 and 1. Okay, so let's take a value that is less than 0, let's say negative 1. I'm just going to sub that into our second derivative. So we're going to get, what do we got up top? So negative 2 times negative 1 gives me a positive 2. And then in the denominator, we have negative 2 cubed, which is negative 8. And remember, all I really care about is the sign of this fraction, which is negative. So in this particular region, we're going to have a concave down kind of shape based on our second derivative test. Next, we want to pick a value that's somewhere in between 0 and 1, say 1/2. So 2 times 1/2. So I get a negative 1 up top. And 1/2 minus 1 is negative 1/2. And if we cube that, we'll get something like this. Okay, so my numerator plugging in 1/2 gives me negative 1, and my denominator plugging in 1/2 gives me negative 0.125. So overall, I have a sign that's positive in this region. So in this region, my parametric curve is going to be concave up. And then last but not least, you want to just finish off looking at this last region here. So maybe we plug in something like 2, and we'll get negative 4. 2 minus 1 is 1. So again, I'm going to get a negative value in this interval. So there's only one interval here where we are going to be concave up. And that's this region. And that's based on our second derivative test. All right, so that is bringing us to the end of our first live stream. I don't have any more new questions to answer inside of my Gmail account. So if you do come up with some questions in the next week, if I have a couple that kind of come in tonight, I might do a quick live stream tomorrow just to answer those questions. Remember, you can send all of your questions to mathquestionshelp@gmail.com, and I'll do a little kind of run through like this little live stream to kind of answer those questions, and it'll be posted for you afterwards on YouTube, so you can kind of go take a look and see how to solve them. All right.